Good evening, and thank you for joining us for this live streamed presentation, Geophysics and the Earth with Bryan Travis. I'm Rick Wallace with Pajarito Environmental Education Center or PEAC, located in Los Alamos, New Mexico, and I will be the moderator for today's talk. Tonight's talk is being recorded. We were able to offer programming at this time because of our wonderful members and donors, and we do thank you. We'll send all of you who've registered an evaluation form after this talk, and we'll use your comments to improve future programs. Bryan will be taking questions tonight via Zoom chat. Type your questions into the chat window at any time during the show, and I will relay the questions to him, probably mostly at the end of the presentation. So, Bryan Travis, tonight's speaker, has a PhD in applied mathematics with a specialization in fluid dynamics. He retired from LANL after nearly a 40-year career in the geosciences and is currently a senior scientist at the Planetary Science Institute. We're very happy to have Bryan with us tonight, and I will turn it over to you, Bryan.
Thank you, Rick, and good evening, everyone. Let's see if I can, whoops. Okay. There we go. Okay, well, tonight we're going to have let geophysics take a look inside the Earth. Basically, we'll be considering large-scale forces that have shaped our environment. I like to remind everyone of the immensity of the universe. I've put the scales of the universe and the galaxy and the Earth in units that I understand, miles, but the numbers in front of them I don't understand. The universe is pretty a mind-boggling number, and our galaxy, the Milky Way, could be one of those smudges in that photograph, and it is also very, very large. And our little Earth would be a microscopic dot in the picture of the Milky Way. But even as small as our Earth is, we live in a very, very small layer, thin layer on the surface of the Earth, only roughly 15 miles thick from top of the atmosphere to the bottom of the oceans and maybe a few mines. So we really need to protect our little planet. So as I said, many processes over various time and space scales have shaped and continue to shape the environment we live in, and we will discuss some of those tonight. Okay, I should define what geophysics is as opposed to geology. Geophysics is a branch of natural science concerned with the physical processes and properties of the Earth and the use of quantitative methods of analysis. Geology, on the other hand, is more focused on observations and qualitative characterizations, but the border between the two has really blurred a lot in recent years, and geologists are making more use of quantitative methods, and geophysicists are relying a lot more on observation and experimentation. Okay. Well, I've spent most of my career down in this corner here of modeling, using observations and experimentation as constraints and ideas on how to improve models of Earth dynamics. So some of the things we need to know about the Earth to build Earth interior models are listed here. Some of the obvious ones, like the size of the Earth, the age of the Earth, internal structure, gravity, energy sources to drive whatever dynamics we're concerned with, initial conditions and boundary conditions, composition of rock types, mineralogy, various properties of rocks from density to thermal properties and elastic properties, and viscosity and water content are important. Well, how big is the Earth? This was a really arrived at very early in our history and in an amazingly simple way. Eratosthenes, a mathematician in 3rd century BC, ancient Greece, determine the circumference of the Earth. Just made a few reasonable assumptions, used a gnomon, which is basically a perpendicular column, frequently part of a sundial, a measuring rod to measure the length of a shadow, and then he hired bemetists, who are basically surveyors. They would go and measure distances for you very accurately to measure the distance between two cities. So the ancient Greeks believed the Earth was round. For example, when ships go out from port and you see the hull disappearing before the sails, then you know there's curvature there. And they also noticed that the constellations of the stars shifted as you moved north or south a significant distance. And there were other indicators. And Pythagoras, 500 BC, believed the Earth was a sphere, a perfect shape. But Eratosthenes basically calculated the circumference of the Earth using geometry and those few simple tools in June of 240 BC. And the way it happened was this. Let's see, just a second, I've got to get the, I can't see my own slide. Okay. Basically, on summer solstice, he noticed that the sun shone directly down a well in the city of Syene in Egypt. And he realized that must, since it shone directly down the well, did not cast any shadows, it must basically be on a radius with the center of the Earth, assuming the well was pretty vertical. And so he realized that if he could, on the same day at the same time, in another year, of course, measure the angle of the shadow that the sun made on a vertical pole in another city, for example, Alexandria, and if he knew the distance between the two cities, he could determine the circumference of the Earth with a simple ratio. So he carried out this experiment and measured the distance, measured the angle to be 7.2 degrees, which is 1/50th of a circle. And then using the ratio that the shadow angle divided by the distance between the two cities would equal the 360 degrees of a full circle divided by the circumference of the circle. So it would just be 50 times the distance between these two cities. And his number was off only by 1% or 2, amazingly accurate. A couple of his assumptions were a little not precise, like Alexandria and Syene were not on a direct meridian, but it didn't matter that much. And there you have it, just a few assumptions, a couple of sticks in geometry. You could determine the size of the Earth. Oops. Okay, the age of the Earth was a little more difficult to determine. We know now the Earth is about 4.5 billion years old, but it took a while to actually determine that number. Be back in ancient Greece, Aristotle, for example, thought the Earth always existed. It was just always there. And there really wasn't any good estimate, at least in the Western world, until, well, I should say a good estimate. There was an estimate in the 1650s by Bishop Ussher, who actually pinned it down pretty accurately. 6 p.m. on Sunday, October 23rd, 4004 BC. Of course, he was using a biblical text as a science book, but I have to give him an A for effort, I guess. Steno and Hooks in the 1660s, 1670s were noticing that the horizontal strata that you see when you drive down to White Rock and the cliffs contain fossils of various different types of fossils, and probably were not laid down all at once. And so each layer, they realized, took a long time to be laid down, and so the Earth must be pretty old. But those were still just qualitative estimates. In the last 250 years, we've started getting some hard estimates, Georges Buffon in 1778 surmised that the planets formed from a comet smashing into the sun, so they were hot initially. He actually did an experiment, looked at, calculated or measured the rate of cooling of small lead spheres and extrapolated that to the size of the Earth and got a number of about 75,000 years. He actually thought the Earth was much older, like 10 million years, based on mountains of chalk, how long it take to lay down those deposits. But he thought that was much too long for anybody to believe it. And then in the 1780s, 1830s, we had the unconformity, the uniformitarianism and catastrophist battles, which are kind of like creationists and evolutionists at the present time. Basically, uniformitarianism assumes that geologic processes occur at the same rate today as they did in the past. The laws are the same. And the catastrophists think, well, things happen rapidly and then they slow down. If you want a good introduction to geology, you should read Charles Lyell's 3-volume set. It's written back in the published in the early 1830s, but it's really a wonderful set of books. Then Lord Kelvin also assumed that, well, a comet must have hit the sun to form the planets and the Earth. So the Earth started out as a hot globe that cooled. He estimated, well, depending on what kind of property values you use for densities and thermal conductivities, could be anywhere from 24 to 400 million years. Then when radioactivity was discovered in 1896, things really heated up. Actually, Becquerel got the credit for discovering radioactivity just before Madame Curie, but actually St. Victor had done it 40 years earlier, and he published it, but nobody paid any attention. Becquerel did the very same observation and got the credit. And Lord Rutherford, 1905, started getting an idea of using radio dating, but his data was pretty unreliable. He got tens of millions of years. Boltwood, 1907, did a much more careful analysis and got 2.2 billion years. People began to realize this is kind of complicated. There's a lot of radioactive isotopes and they form chains, daughter products. And it took them a while to sort it, excuse me, to sort it all out. H.N. Russell of the Hertzsprung-Russell fame in 1921 put his hand to the problem and came up with numbers of about 2 to 8 billion years. Pretty big error bar, but he's getting in the right neighborhood. Finally, in 1926, the National Academy of Sciences adopted the radiometric timescale, and but there wasn't a definitive estimation or determination until 1956 when Cameron Patterson, Caltech geochemist, published his work on lead isotope ratios. It came up with 4.55 billion years. So as opposed to determining the size of the Earth, determining the age of the Earth took a long time, required a number of discoveries and the work of many people. Okay, so how do we know the internal structure of the Earth? Well, basically with seismic analysis. Earthquakes generate waves that travel through the Earth. P waves and S waves. P waves are compressional waves, like sound waves. Shear waves are the S waves, and they involve motions perpendicular to the direction of propagation of the wave. There are a lot of earthquakes around the Earth, and there are a lot of monitoring stations. And over the years, scientists have determined, analyzed the data, and come up with a pretty good estimate of the internal structure of the Earth. And we know that the outer core of the Earth is liquid because it does not propagate S waves. Only liquids don't propagate S waves. And so in combination with laboratory experiments on a variety of minerals and elements over a range of pressures and temperatures, we're able to correlate all the wave propagation information with structure of the Earth. So they could generate profiles of P&S wave propagation velocities versus depth, as shown here, and get pretty good estimates of the thicknesses of the various layers. And here we see a schematic of the cross section to the Earth. The inner core is about 1,200 kilometers radius. The outer core has a depth of about 2,270 kilometers, lower mantle about, and the upper mantle together about 2,900 kilometers. And notice though that the, well, interesting thing here is that the temperature structure of the mantle most of the temperature occurs in the boundary layers. For example, in the lithosphere, top 100 to 200 kilometers, it's defined basically as an isotherm, the bottom of the lithosphere of around 1,500 degrees C. So just in the 100 to 200 kilometers of the crust, you got huge temperature increase. And it doesn't increase nearly as rapidly till you get down to the core mantle boundary, where it increases to about 2,500 degrees C. There's a jump there, and then another jump at the outer core, inner core, where temperature gets up to over 5,000 degrees centigrade. And the pressures are pretty high, pretty intense, up to over 3.5 million atmospheres at the Earth's center. Okay, so convective motions in the Earth, that's kind of what I've been aiming towards here, but how do we know that that's actually happening? Well, there's a lot of evidence: plate tectonics, seismology, hotspots, gravity, energy, lab experiments, theory, and we'll go through some of that. Well, plate tectonics, the crust of the Earth is divided up into about 20 plates. 15 of them are shown here. There's 7 large ones: North Atlantic, North America, Eurasian, African, South American, Pacific, Australian, and Antarctic. And these are resting on the asthenosphere, which is not fluid, but it's warm, it's hot, and the rock can creep. It's fairly plastic so that these plates can move. And the idea here is that upwellings from deep in the mantle are coming up and melting when they get near the surface. The melt spreads out, pushes the existing crust outwards, and as the plates move towards the continental crust, they subduct. The ocean crust is a little denser than the continental lithosphere because it contains more iron, and it may or may not penetrate all the way down to the bottom of the mantle, but in any case, it breaks up, and a lot of it is probably recirculated in the convective cycle. And where the plates subduct under the continental crust, you get a lot of friction as the plate dips down, and so you get melting. Some of the melt rises to magma chambers, 4 magma chambers, and then volcanoes. Plus, as the plate pushes against the continental plate, you get a lot of folding and compression of the continental plate, and you get mountain building. Okay, seafloor spreading. The rates vary all over the world. The mid-Atlantic ridge, the spreading rate is only about 1 inch per year. And but in the East Pacific rise, it's moving quite a bit faster, like 1/2 foot per year. You know, it's going to break the plate barrier. And the plates are moving and they're pushing against the continental plate, and that's part of the reason why you have the Andes Mountains and all the mountain range along the South American west coast. Okay, and hotspots, another possible indicator of convective activity. We know that the Hawaiian Islands their age increases the farther away you get from the big island of Hawaii. And it's believed that there's a source down on the core mantle boundary that's feeding a hot plume up to the surface. And as the plate passes over the plume, you get these hot spots, these volcanoes. And that's been verified in a really extensive study by a professor and a student at UC Berkeley a few years ago. They looked at 20 years of earthquake data, hundreds of monitoring stations, and using the supercomputers, determined the structure of the hot plumes coming up. And here you can see a section of the south of the Pacific that includes Hawaii and Tahiti. And most of these hot spots correspond to hot plumes coming off the core mantle boundary. A pretty impressive computational feat. It's basically verifying what people thought for quite a while. Okay, gravity. Well, Newton published his, or developed his universal law of gravity back in 1680 or so, but it wasn't actually verified or tested until Cavendish published his work in 1798. He wanted to calculate the average density of the Earth. And this came about because of concerns about surveying, which was pretty surprising to me when I learned about this. He knew that surveyors were trying to settle a dispute about boundary lines between the state of Maryland and the state of Pennsylvania back in the 1760s. And he also was worried that the Allegheny Mountains would affect the plumb bobs of the surveying instruments. And so their measurements would be off because they wouldn't account for that. And he had calculated that the error could be as much as 200 meters. So if you were a farmer, for example, and surveyor was going to be off by a couple hundred meters, that could be pretty irritating. But in any case, he wasn't able to actually devise an experiment to solve this problem for about 30 years. But he devised a scheme seen over here on the right. Two heavy lead weights on a wood pole would attract two much smaller lead spheres on a bar that's hanging from a tension wire. And as the small masses are attracted to the heavy ones, the wire resists the twisting. And the small weights would oscillate back and forth, and he could measure this angle theta and also the period of the oscillation. And from that, plus Newton's universal law of gravitation, he was eventually come up with a formula for the mass of the Earth, which is pretty amazing. And his accuracy was within 1% error. Okay, we go from there to pretty amazing ability to measure gravity from space now. Picture on the left shows us the setup for the GRACE satellites, stands for gravity recovery and climate experiments. And basically, we have two satellites, one following the other at 220 kilometer distance. And they're in an orbit about 400 kilometers up. And they send radio waves back at certain frequencies between each other to measure the distance between them. And as the satellites pass over the Earth and the gravity varies a little bit, the distance between the satellites varies a little bit. And they can detect the change in that distance to like within 10 microns, which is pretty amazing. And this is basically an abstract mass on a spring. The second satellite is the mass, the distance between them is the spring. And all gravimeters, just like this one, the trick is in how accurately you can measure the change in the distance of the spring as you go into regions of varying gravity. And they can also measure ice mass, sea level changes, even ocean bottom pressure with this. And the two pictures on the right show changes in groundwater content in Northwest India due to a drought over a 3-year period. You can see the water goes from an excess of a few centimeters down to a deficit of several centimeters equivalent water content. So it's pretty amazing. You can do all this from space with this sort of an arrangement. Gravity maps have been built up with the GRACE satellite, showing the differences in gravity around the world. This is useful for modelers like myself, because if you have a model of the internal dynamics or internal structure of the Earth, you can calculate what the gravity would be at the surface, and you can compare it to data like this to see how far off you are, or use this kind of data to constrain your model. And of course, gravity data is used a lot for more shallow tasks like resource recovery and locating hazards. There's even more accurate gravimeters in the works, like these quantum-based devices are a couple orders of magnitude more sensitive than these. Now, energy source for the amount of convection. Well, we know that the core is hot, the surface is cold, so a temperature difference can drive convection. There's a lot of heat generated by decay of radioactive isotopes, and there's several of them that we know are in the mantle. Of course, a couple of these have short half-lives, so they're pretty much gone now, but they helped heat up things at the beginning. Thing is, these are present in the mantle at low concentrations, but they're pretty much everywhere, and they're always on, so that adds up to quite a bit of heat. Plus, there was heat delivered from meteor impacts back at when the Earth was forming in its early years, and that kinetic energy was converted into into heat. Okay, the convective flow is characterized by the Rayleigh number, which is a ratio of buoyancy to viscous and diffusive processes. So basically, a fluid is more buoyant if it's hotter, because then its density is lower. So it'll tend to rise, like bubbles in a boiling pot of water. Processes that will tend to keep these bubbles or blobs of lower density material from rising include viscosity. Of course, it's a lot harder for a bubble to rise through syrup than it is through water. And also diffusion, heat diffusion. So if a blob is retarded, or if the diffusivity is too high and it loses its heat too fast and its density drops off, and then there's no more push for it to rise. The Rayleigh number is calculated by this little formula. So you can see it depends on the temperature drop, depends very strongly on the depth of the layer, and on thermal and viscosity, density, gravity, and thermal expansion. Now, the important thing about this is that all flow models that have the same Rayleigh number will behave the same, regardless of the space or time scales associated with them. Yeah, I've simplified it. There are some other factors involved, but generally that's the idea. And this just shows some work we did a while back, looking at the Rayleigh number. You know, there's a critical value that depends on the particular situation you're trying to model. If your Rayleigh number for the system that you're dealing with is below this critical value, nothing happens. If it's above it, then you can start getting convective motion. And at low values of this Rayleigh number, above the critical value, you just get steady rolls. And then as the Rayleigh number increases, the convection becomes more vigorous and the rolls start pulsating, and then they break up into plumes, and the plumes start breaking up into really thin, very unsynchronized in time and space plumes coming off very thin boundary layers at the top and bottom of the domain. And basically, internal heating just makes everything happen at lower thermal Rayleigh number. Just makes things unsteadier. A couple of examples from simulations in the past, two-dimensional slice through the Earth. You can see these thin rising plumes that spread out These are temperature maps. This is the streamlines. So flow is going up here pretty fast and not so fast here. And you see the downwelling plumes that mostly don't make it through all the way through the mantle. They tend to fizzle out. Occasionally one will. These plumes are very time dependent. 50 million years later, they've changed quite a bit. Now on this side, I have a more colorful example. This simulation is very similar to these, except there's 2 layers of viscosity. The authors have included the asthenosphere, basically a lower viscosity layer than the mantle. And that's really put a damper on the small downwelling plumes. Most of them don't make it into the lower mantle. Occasionally though, you'll get a big breakthrough. And the upwellings are there, maybe not quite as pronounced as in this single layer case. But recently, high resolution 3-dimensional simulations are become available. This isn't a coronavirus. This is rising plumes coming off the core mantle boundary of an Earth model with a rigid lid. The lid's been taken off so you can see inside. And this has 2-layer viscosity also, a asthenosphere with low viscosity, and then the mantle with the sort of the standard value that we used to use. But you can see lots and lots of thin, irregular plumes rising to the surface, basically like the hot spots. And the downwellings mostly don't make it down to the core mantle boundary, but occasionally a few do break through. Okay, well, we're not done with convection in the Earth's interior. Remember, the liquid iron outer core could convect, and its convection air is called the geodynamo. Generates the Earth's magnetic field. You need 3 things for that to happen: electrically conducting fluid, which is iron, a rotation, and an energy source. The core of the Earth, mostly iron, some nickel, some sulfur, and a few other things. Very hot, 5,000 degrees or more. It's about like the photosphere of the sun. It gets its energy partly from release of latent heat at the inner core, outer core boundary as iron precipitates. You might think that iron might precipitate near the core mantle boundary, but it doesn't, because it depends, the melt temperature depends more strongly on pressure than it does on temperature. So that's why you get solidification at the inner core, not the outer. And flow rates are much higher in the outer core, like 3 meters an hour, which is thousands of times faster than mantle convection, tens of thousands of times faster. The magnetic field is known to flip from north to south pole about every 200,000 years on average, but it's highly variable. So how do we know that? Well, basically looking at magnetic stripes that have been observed in the ocean floor. When magma comes up and solidifies and pushes the ocean crust aside, when the magma cools enough to become solid rock, the polarity of the iron atoms is locked in to whatever the magnetic field of the Earth is at that particular time. And so as more magma comes up and pushes out, you'll get this process of parallel sections of ocean crust that have alternating magnetic polarity. You can see that pretty clearly in the lower right, where the polarity has changed. There's the bar, one direction, and then the negative. You can see that very clearly there are parallel lines that are symmetric about the mid-ocean ridge. And so for measuring, knowing the speed at which the crust is moving, you can determine how long, what a time span there was between the reversals. And I got some slides from Gary Gladsmeyer, who was professor at UC Santa Cruz, And he was also at the lab at Los Alamos in our group, Chip Keller's group, a long time ago. And he was a lab fellow. And he was the first one to calculate a reversal of the Earth's magnetic field. Basically, like right now, the Earth's magnetic field is more or less like a giant dipole magnet with the fields of force coming out of one pole and wrapping around, coming in the other one. So over here, you see between reversals, it's kind of a vanilla dipole magnet. But when a reversal occurs, things kind of go haywire and you've got field lines all over the place. And if you were walking around on the Earth with a compass, your needle would be spinning in all sorts of directions, depending on where you were. And here is a movie of the reversal. So the movie cover, this is the surface of the Earth. Field lines are coming out of the South Pole, going into the North Pole at the beginning of the simulation. It's a little more erratic on the outer core mantle boundary. The simulation covers 7,000 years, but you'll see how the magnetic field begins to become unstable, the interface, and then finally flips around to reverse polarity and then stabilizes. And Gary was the first one to accomplish this feat. It's pretty good because the Rayleigh number of the outer core is extremely high because of the viscosity is so low compared to the mantle. So it was quite an accomplishment. Okay, another comment about geodynamos. Some people were wondering, well, why don't terrestrial planets like Venus and Mars have geodynamos? They have a hot core and they rotate, but the problem for them is they don't have tectonic plates and they don't have mantle convection. Mantle convection, remember, transfers heat more rapidly than just pure conduction. So mantle convection will transport heat out of the core faster than conduction would, which means you maintain a larger temperature drop across the outer core, which keeps the Rayleigh number up and greater than the critical Rayleigh number. So basically, no mantle convection, no or rapidly fading geodynamo. And why wouldn't some planets have mantle convection? Well, Mars is smaller, so its Rayleigh number is quite a bit smaller, but also Mars and Venus probably don't have much water, which affects the water content affects the strength of the rock, mantle rock, and that would increase the viscosity and probably basically mean their Rayleigh number is too small for convection. Okay, so now why would anyone care about mantle or core convection? So just something people like me like to play around with. Well, if there was no convection in the interior of the Earth, there would be less heat loss at the surface. Would that mean a colder surface? Well, maybe a little. Actually, we get most of our energy input from the sun on the surface. But no convection, if we never had convection, means there would be no plate tectonics, no subduction, no continents, no mountains or volcanoes, or maybe only a few, maybe even no oceans. You may just have a swampy surface with a lot of muddy water puddles here and there. And also, remember, if no mantle convection, then you wouldn't have any outer core convection and no geodynamo. And the geodynamo protects our atmosphere from solar wind and cosmic radiation, which would strip the Earth of its atmosphere, just as we think that's what happened to Mars. We actually think it happened to Venus early on, but then it evolved a lot of CO2, which basically created a buffer zone against solar wind and created sort of a mini shield. But still, the damage was done earlier because no dynamo. So basically, in the long run, no dynamo means no life. Okay, other planets, we assume the same principles of physics and geophysics would apply. Mars and the moon, too small to sustain geodynamos. We know there are oceans on the water moons of Europa and Enceladus. In fact, those oceans are much deeper than our oceans on Earth. We know there's a lot of water in the largest asteroid series. And even Pluto and Titan seem to have H2O oceans buried beneath their frozen liquid nitrogen or frozen nitrogen surfaces. And how do we know that? Well, for example, for Europa, the magnetic field measurements in the flyby, I think it's Cassini, indicate that there's a lot of water underneath the ice surface. And plus in Enceladus, you can see the water spray coming out of fractures, geysers coming out of fractures at the south pole of the moon. Pretty astonishing, since Enceladus so small, you think it'd be frozen solid. Anyway, Lano, I think I have time to go through this. We did some experiments of our own because we wanted to look at possible convective processes in Mars and Enceladus and Ceres. And so actually Mario Graal and Dan Reisenfeld set up the system, instrumented it really well, got a lot of good data. Here's a little movie clip from one of the runs. And you can see that we get the plumes as our models predict. And in this case, Rayleigh number is high enough that the plumes are unsteady. They oscillate back and forth. And we think that's actually may be a possible model for what's happening on Ceres. There's a big crater called Akator. There's a bright spot in the middle of it. And spectroscopic analysis indicates it's salts that have, so we think there's a salt, brines have come up and the water's evaporated, leaving a salt deposit, calcium carbonate, I think. Similar to one of our experiments where we had brine convection in those tanks with a cold surface, and we get plumes that penetrate the surface and about the right size. And this is the depth of the Syrian crust. Anyway, it's fun to see some of these things possibly coming together and being possible explanation. Future directions. Well, for deep Earth, models are getting to the point where they can include plates along with the constraints on gravity and heat flow and variable viscosity in the simulation of mantle convection. Takes a lot of computer power to do that. But some of these have already been coupled together to mantle convection. And in the shallow Earth, it's just simply a lot more data coming in from satellite networks, buoy networks in the oceans, all kinds of imaginative ways of measuring things like laser Doppler vibrometry from orbit. The models are getting better. Data analysis methods are getting better. And one thing I wanted to talk about is fractures. Fractures are something that really is a hassle for anybody modeling processes in the near surface, because they really impact fluid flow, water, oil and gas, contaminants, and also stress strain problems. If you're trying to calculate movement of the Earth, you've got to deal with some cases lots and lots of fractures like this. I think this is somewhere along the coast of Wales, incredibly fractured system. And you can try to average the effect of all this, but my own group at the lab has developed a really world-class breakthrough modeling capability where you can put in all the fractures that you want, zone up grids on all these fractures and on the interconnecting channels, and have flow and reactions and stress strain simulations on really complex systems like this. It's really quite an amazing feat. And I guess I can finish here with inverse problem. Mantle convection, generally, when we start the problem, we're just looking at what's the characteristic of the flow as Rayleigh number increases or as some other property changes. we're not too concerned about the initial condition because it generally fades away after you start the simulation. But if you're trying to simulate the actual Earth, you'd like to be able to start from some point, not at the very beginning, because it takes an awful lot of computer power to simulate 4.5 billion years. But at some point in the past where you have a good estimate of the situation and then work forwards. And there's actually a way to do that mathematically, basically running the models backwards, but not in the naive way. Some ways to do that that are mathematically correct. And so we had a graduate student and a postdoc and myself who were involved in this a few years back. But basically, using the Terra code developed at Los Alamos, and using the internal present day structure of the Earth and present day plate motions and the reconstruction of plates back 100 million years, we're able to do this inverse method to determine a pretty good state of the internal state of the Earth 100 million years ago. So, and this is an iterative process. In each iteration, the initial state is improved until you get to a point where the error is not changing much. So here at the end, we have the present condition of the Earth, and here's what the Earth needs to have been like 100 million years ago to get to this, to evolve to this point with the plate motions that were also applied. So this is very computationally intensive because you have to run the forward model, which is pretty involved itself, a few hundred times to get a really good answer. In any case, I think I've come to the end, and thank you for your attention. And if there are any questions, I'll be happy to entertain them.
Fantastic. Thank you, Bryan. That was great. Very
Sorry,
interesting
my
talk.
voice is kind of rattly.
That's okay. It came through just fine. We do have some questions,
Okay.
and I'll start with a few of these. Let's see. Actually, let me start with this one. Steve asks, what did the Russians learn from their deep borehole into the crust? Do you know?
I had forgotten about that. The MOHO is the Mohorovic discontinuity. It's down a number of miles. Not sure if they got to that point or not. Just a second. Yeah, I think they're probably trying to get down to the boundary between the Earth's crust and the mantle, which is about 10 or 12 kilometers down. But I'm not sure if they made it, probably. Sorry, I don't know the answer for that.
That's okay. We'll let Steve and others just go to Google and see what they can find out. Let's see, another question. You mentioned the GRACE satellite system for measuring gravity and gravitational anomalies around the Earth. Could a similar system, or do they use a similar system for space probes going to other planets to look at gravity fluctuations around those planets, and does that help them map things like water and other things, density variations around other planets?
So could you repeat first part of that again?
Yeah, so you were talking about the GRACE satellite system measuring the gravity anomalies on the Earth and being able to detect things like water and other things. Are there similar instruments on space probes going to other planets that are used to look at gravitational anomalies on planets or asteroids or things like that to try to look for water and other things?
Yeah, for example, in Ceres, the Dawn mission, and measured gravity, produced a gravity map of Ceres. So that gives us some idea also that interior is not uniform, that it's It's probably has some convective motion going on. And yeah, NASA's been a little flaky the last few years as far as funding things, but I know there are people who want to set up a similar system around some of the water moons and around Titan. Titan looks like Earth, except it's incredibly cold, but it's all based on methane and ethane. They're the equivalents of water on Earth, and a rock is water ice. It's so cold, the water ice is literally as hard as rock. It's a very interesting place, but it's got rivers and mountains and erosion and all that on it.
Okay.
I looked up the Mohorovic, the Russian drilling, and they did get down to a little over 12 kilometers. So they're at or very close to that Mohorovic discontinuity, the bottom of the crust. Now, I don't know what they actually determined, but looks like they got just about down to that point.
Interesting. Okay. Another question. You mentioned hotspots as a reason for things like the chain of islands in Hawaii, as the crust moves over a stationary plume. But one would think that with the Earth's rotation and all the convection going on in the mantle, that these plumes might move around a little bit and not be stationary in one particular place as long as it would take to make a chain of Hawaiian islands. Why are the plumes so stationary?
Well, actually, rotation is not that important for the plumes, for the mantle convection. And we worried about that when we were building our models, but it's not that important. If you're in a fluid, now for the, excuse me, for the inner, my voice, for the outer core, rotation is important because its viscosity is so low, it's really moving fast. And the Rossby number is in a range, which is another non-dimensional number that characterizes rotating systems. And in that case, the Rossby number is in a range where rotation is important, but for the mantle, it's not.
Okay, so the plumes are stable for long periods of time.
Yeah, well, long periods of time can be, tens of millions of years, and then they fade, and then another one pops up somewhere else.
Okay. All right. Let's see. Julia asked, does the upwelling pushing the crust apart, like in the Middle Atlantic Ridge, exactly balance the subduction or under the continents, or does the diameter of the Earth change to be smaller and then larger depending on which of those mechanisms is dominant at a given time?
Oh, that's a very good question. Well, probably not exactly. It doesn't exactly balance. At the ridge, you get a ridge, an elevation, and then the ocean sinks, the ocean depth increases toward the continent. And there's something called slab pull because the slab is denser than the continental crust, continental plate. It sinks below, and it does tend to pull some, but you can also calculate the drag on the plates from mantle convection currents that are flowing past the plate, and there's significant drag from convection. So it's a little bit of both. I mean, the upwelling is pushing and the slab subducting is pulling, but it's also getting pulled or pushed by convective drag on the bottom of the plate.
Okay, wow. All right. Well, let me ask if there are any other questions. Those are all that I see in the chat at the moment. We'll give people a few more seconds. And then we'll close out. Okay, those look like all the questions that have come in from the viewers. We'd like again to thank Bryan Travis for sharing with us tonight. A very interesting topic, a little more complex than most people think of when they just think of geology. Um, and I'll also mention that next week, Galen Giesler will be using the special effects available in our planetarium to do a live show in the planetarium discussing the threat to Earth from asteroids and what we might be able to do to prevent an extinction level event from asteroid collisions. Those things that Bryan mentioned that can heat up the Earth, among other things. So, thanks to everyone for tuning in, and good night.